Assalamualaikum warahmatullahi wabarakatuh. So we are from group 2. We'll explaining a basic application of bioreactor in fermentation process. So our members is Lim Yi Chua Kayang, Ana, Isma Suhana and me Adam. So I will explain a bit about the bioreactor. So bioreactor is the IKA Habitat Bioreactor is a modern benchtop system used for a lab-scale bioprocessing. It functions as a 3-in-1 platform, having a bioreactor, fermenter, and photobioreactor with a module design that allowing flexible setup for growing microorganism, cell, and also algae under control condition. It also features an automated control of key parameters like a temperature, pH, and dissolved oxygen, along with sensor and pump for precise operation. This makes it a smart and versatile system that ensure efficient, stable, and reproducible experiment result.
Alright, so now this is a bioreactor. First of all, we need to autoclave it. So first thing we need to move is the vent. So this is a vent. To remove it, you just have to unscrew the bottom and the top, and then you slide it out. Slide it out, take it out, and then you put it on the table. Alright, so now this is the motor driver which we cannot autoclave, so you just remove it. So first you need to unscrew, then you take it out. So you put it one side to the table as well. Secondly, this tool at the bottom is a level and anti-fold. So what you need to do is also unscrew because they cannot be autoclaved. And you have to realize that it is on the same level when you fix it back.
The second part inside 你还要 take out 吗？不是 take out and explain the component inside this one first 吗？
Into the anti-foam, you realize that it is connected to the top level here. So which means that we need to remove both sides. It's connected to the anti-foam here, which means you just have to unscrew. Okay, so it's out now. It's out already. Secondly, you have to remove anything that is on top. So this is for air. Air connects to the spudger. So you just put it back on here. Your acid that is connected to this machine, also you just have to remove it and put it down. This is your temperature machine, so you just plug it up also. Gently. Okay, it's out. Then we have this dissolved oxygen.
Oh.
Okay, it's out now. Okay, so water you just have to unscrew. Okay, so you don't take this out yet because water will come out because there was water inside there already. So now you have to just unscrew all this. Okay, unscrew.
Okay. 1, 2, 3, go.
Alright, so now we're removing it. And there is an O-ring at the bottom here, which is to make sure that the lid doesn't crack the bottom of the bioreactor. Okay, so now we're going to remove the water. So we just have to unscrew this one, the bottom and the top. Okay, so we can pour all the water away and we will put it back. Yes. And in order to screw it back properly, you have to do it together because there are 3 screws. So make sure that it's aligned properly. Screw it tight. Done. Okay, so now we realize that there are like open exit like holes. We need to either use a pipe, so there will be a kind of like a silicone pipe that you will connect to, and then you will clamp. So the rest of it you might either use aluminium or anything to cover it, so that when you autoclave, nothing goes in or nothing comes out. So at the end, you just have to take this whole thing and then you just bring it over to the autoclave. We're gonna put everything back so that we can put our media and everything. First things first, we will put back our WAN, which is here. So just slide it back in. And then screw it. And then remember we have our motor driver. You can just put it on.
Motor driver.
Screw it back. We have the empty foam level. So this one, the one without lights, you can put it one side. So there's this one as well. So the one with the light already. Make sure that you put it on the same level here. Then we screw it back. Now once that is done, we can do the water first because this is your pipe. Make sure to put the bottom one first before you put the top. You just clip it. When you hear the sound, that's it. So now you see water start filling up, right?
Yes.
Water filling up. So now you have to clip everything back on.
This is for the level. This is for the temperature.
Spudger.
For the spudger. pH 1. We need to remove the cover.
So this is the cover. This is the pH one.
And we screw it up.
And then this is your harvest. So next time there will be a pipe. The pipe you can use a syringe. This is the control of the bioreactor. Go temperature. We want to do 35, but it's not on yet, or it could be auto. Then we press OK. So you see green means it is working. So the water will heat up the temperature, and then pH you can set, your oxygen you can set, and then if you realize there will be acid or alkali or base to maintain the pH of the sample. So what you do is you connect it to this machine here, and then you plug it here. You have to do it according to the sequence. So you all connect to this one here. Okay? So now it's green, so means everything is working.
Alright, so here we can see a top headway of a laboratory benchtop bioreactor, which is commonly used for cultivating microorganisms or cell cultures under controlled conditions. So at the center is the agitator or motor shaft connections, which drives the internal impeller to ensure proper mixing and uniform distributions of nutrients and oxygen throughout the culture medium. The system also includes several important parts. The 4-in-1 feed port is used to introduce nutrients or media into the vessel, while the reserve port acts as a backup connection for additional probes or sampling lines when needed. So we can see the right side picture. It shows a sensor and probe connectors that are connected to monitoring devices such as pH, dissolved oxygens, and temperature probes, allowing the researchers to continuously monitor culture conditions in real time. So in addition, the tubing lines with tension clamps, it helps to regulate the sterile flow of gases and liquids into the reactor. So finally, the hot surface warning symbols it can show in the bioreactor indicates that the equipment may reach high temperature during sterilizations of operations. So overall, this heat plays a very critical role in maintaining a stable and controlled biological environment for efficient fermentations and cell growth. Yeah. So this is a third close-up view of the same bioreactor headblade rotated with focus on the tracking, safety, and physical management parts of the vessel. So as you can see, the first is the level, which is a port for the level sensor probe to detect foam built up or ensure the liquid volumes do not overflow. And next we have the baffles, which is an entry point where the internal vertical plates attach to disrupt vortex formations and improve mixing efficiencies. And then we have the temperature. It's a thermal port designed for a temperature sensor or thermocouple to monitor internal growth heat. And the second one, We focus heavily on the online monitoring sensors and primary gas or liquid delivery ports of the bioreactor head plate. So as you can see, we have dissolved oxygens, we have the level port that position adjacent to the DO port, and then we have the BNC and multi-pin sensor connectors. So what's a DO? DO is a dissolved oxygen port that holds a optical or electrochemical probe that monitors oxygen levels in real time. And this function is very critical for aerobic cultures like bacteria or yeast. And as you can see, the level port uses a position adjacent to the DO port, and this is used for a level or foam sensor probe to prevent the liquid overfills. And we have the BNC and the multi-pin sensor connectors, which is like a metallic one, push and twist connectors plugged in here to transmit all signals from the internal pH or DO sensors back to the main control tower. So this is the exhaust condenser on top of the bioreactor. It cools down the hot exhaust gas so evaporated liquid will drip right back into the vessels. So here how it works. The hot gas will travel up throughout the stainless steel body, which connected to the vessel using the braided tubing at the bottom. So to cool it down, the horizontal metal heat sinks fins pull the heat away. At the same time, the cooling fans behind the guard blow air across the fins to keep everything running efficiently. The next panel we can see this is the gas supply and the sensor panel on top of the main control unit. It controls the exact mix of gas pumped into the bioreactor to keep the culture healthy. So on this panel you can see the quick connect ports for four main gases. We can see the air for general growth, oxygen for extra boost, nitrogen to remove the oxygens, and carbon dioxide to adjust pH. The clear tubing hooks the clear tubing hooks up to these ports to carry the gas to the tank. Right above them is the black temperature sensor plug, which tracks how hot or cold the liquid is. And in this slide, this view demonstrates the core culture vessels of the bioreactor systems, wearing a double-walled glass jacket for precise temperature regulation. Thermoregulated water recirculates from the control unit through the insulated white tubing, connected securely to the glass port via a fluid type, the red G ultralight cap. So inside the chamber, the stainless steel impeller shaft and metal plates ensures the uniform mixing and prevents the vortex formations. At the base of this vessel, the fluid enters through the lower jacket connection, introducing the water from the bottom, force it to rise upward, ensuring highly even heat distribution throughout the culture. The lower impeller blades continuously spin to keep cells in suspensions, while the graduated markings on this glass allow for accurate volume monitoring, and the entire assembly is stabilized by a heavy-duty support stand and clamping knob. And finally, we will go to the setups that shows the disc filters, and it functions as the prevent contaminations or contamination control and sterile gas exchange. The disc filters is integrated in line with the flexible tubing. So when you see there's is also the critical components and ports that wrap in the aluminum foil. So it is a standard procedure to shield light sensitive media and maintain the sterility and connection points during and after autoclavings. So the entire press assembly is secured by a robust metal support structures, while the utility lines in the background supply the necessary power and temperature regulations for the system.
Belok kan? Nak bagi tu nak angkat. Kita terus kan? Ha. Tadi ya, bagi dia.
Kena clam tak?
Sini plan, sini cable tie.
Okay. Okay mà.
还要讲吧。
You kelonggar lah kena kasi play.
Ada apa? Yang oh this one. Sorry,
sorry.
你们可以猜下面的角。I mean temperature 的。
Oh.
Pasal.
Ini apa?
For sampling.
啊，
我不确定，我不确定。
Buka sikit ujung lah. Macam tu. May I sudah sikit. Ujung je. Okay. Cucuk. Bagi dekat.
Hi, so in this presentation, I'll walk you through the result of our overnight yeast inoculation in a bioreactor. We monitored three key parameters, which is the microbial growth, glucose consumption, and ethanol production. So this result review how the yeast responds to different nutrient levels and bioreactor conditions. So as you can see, for group 2, which is our group, the optical density increased steadily from 0.67 to 1.39 over 20 hours before dropping at 24 hours. The biomass peaked around 1.16 mg per milliliter, showing a clear growth curve with a strong log phase between 2 to 10 hours. And for group 8, the growth started higher at 0.76 and continued rising to 1.23 at 24 hours. The biomass reached about 1.07 mg per milliliter, but the growth curve was flattened, suggesting slower metabolic activity despite more yeast extract. So as you can see from the figure 5.3 and 5.6 in the next slide, you can noticing how the group 2 will show the graph from the group 2 showing a sharper log phase, while group 8 the growth is more like gradual. Yeah. And for the glucose consumption for group 2, which has 10 grams of yeast extract, the glucose concentration dropped from 0.896 mg per milliliter to 0.099 mg per milliliter over 24 hours. This steady decline reflects active substrate utilization. While for group 8, which has 15 gram yeast extract, the glucose started higher at 1.104 mg per milliliter and decreased to 0.088 mg per milliliter. The consumption was lower initially, but eventually reaches a similar endpoint. As you can see in the next slide, which is the figure 5.9 and 5.10, group 2 shows a smoother decline, while group 8's curve is more scattered. For ethanol production, for group 2, the ethanol concentration rises from 0.16% volume per volume to 0.26% volume per volume. Yield increased consistently, reaching 2.63 by 24 hours, a strong indication of efficient fermentation. For group 8, the ethanol production was irregular, It started at 0.17% of volume per volume, fluctuated across time points, and ended very low at 0.008% volume per volume. The yield pattern was unstable, suggesting stress or inhibition. As you can see in the next slides, Group 2 shows a clear upward yield trend, while Group 8's ethanol curve is inconsistent.
Alright, our group 2 shows the growth of microbes, specifically yeast cell in the graph, where we can observe the growth phase of microbes in the bioreactor over time. And group 2's graph of biomass against time starts from the log phase to the stationary and until death phase, while we can observe in group A, their growth phase starts from log phase until it reaches stationary phase, and then of growth phase over a period of time. So with this graph, we can obviously see that the growth pattern of microbes is different in both bioreactors and at different conditions. These two graphs shows the log phase of microbial growth, and based on group 2 result, we can obviously see that there is an exponential growth of microbes at the log phase, which has the equation of y equals to 0.0237x plus 0.8899, which gives a r squared value of 0.951. And group 8 has an equation of 0.2136 ln x plus 0.8243 with a r square value of 0.9194. So in comparison, we can see that there is obvious differences in biomass growth against time, and we can observe that the microbials actually does obtain sufficient nutrient and are growing well in optimum condition during the time of the second hour and the time of the 2 to 6 hour as well in both kind of bioreactors. And nutrients such as micro nutrients and macronutrients of the media is sufficient for the growth of microbes while maintaining the optimal condition of the bioreactor, such as optimal temperature, pH condition, agitation, and airflow. Okay, so now we will look into the glucose consumption. And through this experiment, we have actually tested the glucose consumption using DNS, and the result has shown that the glucose consumption will decrease with time, and this indicates that the glucose consumed by the microbes in both bioreactors has increased over time as well. Hence, the lower the concentration over time will indicate that the lesser the glucose is in the nutrient broth as well. So we can see in both graphs that group 2 does show a more consistent result, and group 8 as well does show a decrease in pattern of glucose consumption. Hence, the lower the concentration of glucose in the bioreactor due to the constant uptake of glucose from the nutrient broth will indicate that the microbe is actually consuming glucose within the bioreactor itself. Okay, in comparing between group 2 and group 8's graph of concentration of ethanol against time, we can see that there is a difference in fermentation dynamics, where group 2 shows a gradual increase from 0.25% to a peak of 0.35% at 6 hours. So we can see that there are fluctuations of a dip and rise from hour 12, and it will eventually stabilize around 0.3% by the 24 hours. This suggests that ethanol production under relatively stable condition for group 2. But when you look at group 8, you can see that there is obvious fluctuations where there is rapid rise and dip within the graph in itself. And overall, group 2 demonstrates a more superior performance with higher peak concentration and lower stability, while group A reflects a more inefficient fermentation that emphasizes the importance of optimizing the condition to balance out the rapid production of with sustained yield. Group 2 findings actually imply that the ethanol production is relatively sustained and stable. After some fluctuations, the system maintained its moderate conditions again. In Group 8, we can see that the findings imply that the ethanol production is quite short-lived after an early burst of dip and rise in ethanol, and we can understand that the ethanol is consumed and degraded and produce heads and halts and leading to near depletion as well. Okay, so now is the last part where ethanol yield is looked into. So the ethanol yield for Group 2 profiling and Group 8 profiling reveals that there is a contrasting rate of production and efficiency. Group 2 displays a more steady upward trend and with regression, and the equation as shown in the graph is y equals to 0.898x plus 0.0748 with a high coefficient of r square equals to 0.9055. Which indicates that it's a consistent and predictable increase in yield over the 24 hours. And this suggests that the fermentation condition is a lot more supported in gradual outward trend and as well as more stable ethanol accumulation. In comparison, if we look at Group 8, it exhibits a steeper slope with the equation of y equals 0.1549x minus 0.5322 with an r square value of 0.8401. This reflects a faster rate of ethanol production with a greater variability. Although Group 8 does achieve a higher yield, however, the lower fit of regression line implies that it is less stable in the process. Taken together, Group 2 and Group 8, Group 2 is definitely more reliable and sustained, and it produces ethanol output that is also slightly more stable, while Group 8 demonstrates a rapid production and may be less controlled, which highlights that there is a trade-off between the speed and consistency in the fermentation performance between Group 2 and Group 8. So that's all for discussion.